In this lecture, let's look at the mathematical induction to prove some identities here. The first one is to prove the following equation is an identity for all natural numbers. Basically right here is we want to prove the left-hand side equals right-hand side for all n. Okay. Basically, here n can be 100, can be 200, 300. Okay. Then probably it's difficult if you add one by one. You have to use a formula to do it in a smart way. Alright? But if this is true, so we got to prove this first. Now, we know 1n equals 1 is basically 6 to the first on the left-hand side. So n is 1, the left-hand side is 6. Right-hand side is what? Is 6 times quantity 6 to the first minus 1 divided by 5. 6 to the first is just 6. 6 minus 1 is 5. 5 cancel each other. So you have the answer is 6. So it appears that the above equation is true for n equals 1. There is no problem. Then you may think, let's try 2, 3, 4. But all you did right here is for the finite number. Okay? Then if you stopped anywhere, people may think that's the only cases you proved. You didn't exhaust all the natural numbers. Okay? So someone may be afraid to use this formula. So we want to prove this is true for all natural numbers. We like to do it in the following way. We assume the equation this one is true for n equals k. So you replace n with k. Please note right here, k can choose at least 1 because, we have proved this is true for n equals 1. So we let k can be 1 at least. So this one is valid. Okay? Assume the equation is true for n equals k. Then we replace n with k. So we may say, then this is true. Okay? Now, if this is true, we want to prove is that this is also true for k plus 1. So here I wrote 1 needs to show 6 plus 36 plus 216 plus ... plus 6 to the k plus 1 equals 6 times 6 to the k plus 1 minus 1 over 5. This is the one we want to prove, and this is the one we assume is true. Okay? Now, let's see how to prove this one. Starting from here. This left-hand side is 1 term less than this one, because here the term before it is 6 to the k. Before 6 to the k plus 1 term before this one is 6 to the k. So then we do is we add 6 to the k plus 1 on both sides of this equation with star, because we assume this is true. So what we did is add 6 to the k plus 1 on both sides of the equation marked with star. left-hand side, you add it. You add 6 to the k plus 1. Then left-hand side is going to be this one. So then we want, when this quantity is added by 6 to the k plus 1, we want to show this one can be written in this way. Or I want to show this one equals that one, and then we are done. But you know, right here, if you want to add those two together, you want to have you want this one to have a denominator 5. So then you may do is 6 to the k plus 1 times 5 over 5. And the denominator will come to be true, well, to be the same. Okay? Now, then this one you go to do distributive property is 6 to the 6 times 6 to the k minus 1. You do is 6 times 6 to the k, which gives you 6 to the k plus 1 for this one. Okay? So basically it's like this. So you see 6 times 6 to the k is 6 to the k plus 1. And then 6 times negative 1 is negative 6. Alright? Okay. Now denominators 5, 5 are the same. You keep it. 5. Alright? And then 5 times 6 to the k plus 1, you write in this way. Okay. Here is 5 times 6 to the k plus 1. Here is 1 times 6 to the k plus 1. Because you know 6 to the k plus 1 is 1 times 6 to the k plus 1. Now you may add this 5 with 1, so you get that. 6. 5 plus 1 is 6. Okay? So those 2 tens can be combined like 6 times 6 to the k plus 1. Minus 6, you keep it. Now, 6 times 6 to the k plus 1 minus 6. Remember, 6 again is 6 times 1. Okay. Then you can pull this 6 out. Then we'll have a 6 to the k plus 1 left. And here you have a 1 left, and it's subtraction over 5. And this one is exactly the one right here. So starting with the equation star, we have proved this is really true by those steps. Then what? Then you can say that hence the equation is true for n equals k plus 1. Okay, starting from n equals k, you can prove the equation is also true for n equals k plus 1. Okay. Now, if k here was 1, you basically have proved n is 2 is also true. And this loop can never end. You see that? Okay. We assume this is the base. And then k can choose at least 1. And then starting with k, we have proved k plus 1 is also true. So if k is 1, k plus 1 will be 2 is true. Then you go back, k can choose 1, 2. And then by the same process, n can be 3 is also true. So then this k can choose 1, 2, 3. And then through this same process, you get k can be true. K plus 1 is 4, so n equals 4 is also true. So this loop can never end because of these few steps. That's very important steps. And people can be convinced. We can conclude, therefore, the equation, this one, is the identity for all natural numbers. Okay? Yeah, that's the thing we want to understand in mathematical induction. By the way, you may wonder, how did we actually get that? Yeah, recall this is actually the geometric sequence. For the geometric sequence, we can actually get this formula. Okay, so we get this formula and we can prove it, and then people then trust math. Okay, yeah, please review this lecture. I'll see you next time.